Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I'm here today with Doug Finke. He's the founder of the Quantum Computing Report. Doug's been involved in computer and semiconductor and storage industry for over 30 years, and he's witnessed and helped drive the birth and growth of a lot of technologies during that time. So he's become fascinated with quantum computing, as I have and many others have. And so I wanted to ask him, since he researches the field, what's real and what's speculation. So Doug, thanks for coming.
Yeah, you're welcome. It's nice to be here.
Yeah, so if you would, for listeners, can you give them maybe just a quick overview of what's different about quantum computing versus traditional?
Well, the way I typically describe it is, for the most part, with some exceptions, the classical computers we use today is really all based on 19th century physics. Things like, Ohm's law, electrons, those types of things were all, physics principles that were discovered, in the 1800s. And the semiconductors is perhaps an exception there, but the very first computers were built with vacuum tubes, and that again was all 19th century physics. What happened is, in the 20th century, in the 1920s and 1930s, a lot of very smart scientists like Einstein and Bohr and Heisenberg and many others, they came up with some new physics principles that were different. That was called quantum mechanics. And specifically, there are a few attributes, a few phenomena in quantum in that quantum mechanics that they discovered. One was called entanglement, where you have essentially two particles or two things that are linked together. And the other is called superposition, where you might be able to have this thing that we call a qubit, which is a quantum bit that actually can be in a mixture of a 0 and 1 state all at the same time. And it turns out that the computers that we have today, the classical computers we have today, do not take advantage of those two quantum mechanical phenomena. And really what quantum computing is about is people have started to figure out ways where they can solve various computational problems and design machines that actually take advantage of those two phenomena, the entanglement and the superposition. And in doing so, they can solve certain problems at a much, much higher performance level than you can with classical computers, which do not use those phenomena. So that's the fundamental change, is that you're just taking advantage of more physical principles from quantum mechanics.
And I guess the goal is you get a multiplication or an exponential ability to look at multiple facets of a problem, I guess you could say, as you assemble qubits together. So I guess it exponentially rises, to the power of 2? You get 1 bit, 2 bit, 3 bit, or is it more than that?
Yeah, the reason that people are pursuing this so aggressively is because you can get massive improvements in performance. Now, it does depend on the problem. Some problems will indeed give you what's called an exponential improvement in performance. Some may be less. It depends on the specific problem. But the way to think about it is that, in 30 years ago, high-performance computing really went from a single-processor design to a multi-processor design, where you have, thousands and thousands of processors working on the same problem, and that's called parallelism. The quantum computing essentially it allows you to do what I call a weird form of parallelism, where indeed you can, because you have the ability, these qubits, to be in state 0 and 1 simultaneously, and then when you gang them together, you can actually sort of indirectly perform a lot of parallelism in your algorithms, and that's why people are able to achieve some of these really high improvements in performance.
And the entanglement makes the parallelism dependent upon all the elements of the parallelism, so that I guess you can get this huge set of possibilities that all can be tried at once, right? Is that
Yes.
a way to put it?
Yeah, that it allows you to do a lot of things at once, and it's a combination of both the entanglement as well as the superposition. But the important thing to understand is that fundamentally, quantum computing is also a probabilistic type of technology where it will do those calculations and then give you a range of different answers with different probabilities associated with those answers. So the key in designing a quantum algorithm is, as some people say, you sort of choreograph the various quantum gates such that the answer that you're really seeking comes out with the very highest probability. And that is how those algorithms work.
Oh, so you don't get a definitive answer, you just get a set of answers with probabilities assigned to them?
Yeah, and you can arrange it so that the answer that you want is very, very high probability, and the answers that you don't want are very, very low probability. But the other thing that is very important to understand about this technology is that the error rate in these qubits is very, very high. They're very, very fragile, and they will go through a process called decoherence, where maybe they'll start in this superposition state, which is again the mixture of 0 or 1, but after, depending on the technology, after a few microseconds or milliseconds or maybe a few seconds if you're lucky, it'll collapse to a 0 and 1. And the magic is actually when those qubits are in that superposition state. So it doesn't last very long, and you have to be really, really clever about figuring out how you can get a useful computation out of a machine that may only be able to last 90 microseconds or so. So it's a real challenge, but the engineers are working on it, have come up with some very clever ideas on how to address that challenge.
Yeah, I've heard the computers need to be cooled tremendously. They need to be shielded. I mean, can you go into, have you seen any of these computers up close? Have you visited any of these companies? And if so, what have you seen? Or at least in articles, what have you seen? What do they look like, the computers? How do they appear to function?
Yeah, I have seen several of them. So there are different technologies. So some require this supercooling, some do not. But the ones that are, let's say, in the lead today, let's say machines from IBM and Google and Rigetti, they do require taking these qubits and putting them under an atmosphere in an environment that has as little external disturbances as possible. So the environment, of course, is in a vacuum. It is shielded from magnetic radiation. You don't want random radio signals coming in and disturbing these qubits. And they are super cooled. They use special refrigerators that are called dilution refrigerators. And these refrigerators, they're $500,000 and up. So they're very, very expensive, but they're able to cool these qubits down to something like 10 or 15 millikelvin, which is just above absolute zero, and it's thousands of times cooler than the temperature in outer space. But by cooling them, it eliminates any possible problems with the qubits collapsing due to various thermal phenomena. So they're doing all these things to keep those qubits, and the term is called decoherence when they collapse, to keep the coherence time as long as possible so they can do high quality computations while the qubit is still in this superposition state.
What causes qubits to decohere or to cohere in the first place? Are you able to explain that?
It's just the external environment sort of the way I might describe it is, the way to think about it is you take a coin. Let's say you take a penny and you put it on the table, it has heads or tails, and that would be like 0 and 1. But what you can do is you can spin it on your table, and for several seconds, it'll sort of be in this state where it's neither 0 or 1. It's sort of a combination of those. But after a few seconds, it just collapses. In the case of the penny, it would be due to gravity. But that's essentially the way to think about these qubits, is that you put them in this state, the superposition state, you do your various calculations, and you try to get it all done before the qubits collapse or before they decohere.
What the companies that you've seen, that some talk about, like 40 qubits or 60 qubits, or why does it get so much harder? Why does it seem to get so much harder as you try to get more qubits involved? Where's the breakdown? Is it, I don't know, are there temperature fluctuations that cause decoherence, or what do you think it is?
Well, as you scale up the number of qubits, there are several challenges that people have to deal with. So right now, probably the leading machines have 53 qubits, at least in the types of machines that IBM and Google do. They both have 53 qubit machines. And in order to control the qubits, you need to basically control them with microwave pulses. And the microwave pulses start at a piece of electronic equipment called a waveform generator that is actually at room temperature. And each qubit has to snake a couple of wires, 2 or 3 wires, down from that room temperature electronics all the way down to the qubits. And essentially that wire will start at room temperature and go down to this 50 millikelvin that I was talking about. So if you ever looked at a picture of one of these things, they do look like a rat's nest. I mean, they have hundreds of wires going down, and given the thermal, the very rigorous thermal constraints, it's a big engineering challenge, just a mechanical engineering challenge to figure out how to do that. And they've done that, and there are technologies that people are developing where you might be able to do some of that in other ways with integrated circuits that run at low temperatures. The other issue that people have is something called crosstalk. So when you have an array of qubits that are sitting next to each other, the problem is that there is a little bit of unintended interference when the qubits are doing their thing. If you want one qubit that's doing a particular gate operation, or it's doing what's called a 2-qubit gate operation with a thing next to it, it could impact the operation and the state of a qubit that's sitting a few places away. So that's called crosstalk, and that's not good. And the other problem is that if you're not careful, as you increase the number of these qubits, the crosstalk gets worse and worse and worse. So it's harder to control. The other thing is that as you these are made with a semiconductor-like process. So as you increase the number of qubits, you have what's a larger die size. So it's a larger physical area, and maintaining process control with larger die is a little bit more challenging, as well as the thermal control to try to keep a very constant thermal over a larger area is a little bit more challenging. So that's what all the engineering is. The industry has made phenomenal progress in the past several years. When I first started the Quantum Computing Report 4 years ago, IBM had just announced a 5-qubit machine. So just in a few years, they've increased it by an order of 10. And that rate will continue for the next several years, maybe probably the next several decades. But there's just a lot of nuts and bolts engineering that's required to continue those increases. And again, it's really a challenge to increase the number of qubits while maintaining or even improving the quality level of the qubits. That's the challenge.
Well, is there a trade-off between either physically isolating each qubit or distancing them? And having them, maintain coherence and not have crosstalk? Or does crosstalk not really respond to those kind of things?
Well, yeah, certainly if you spaced them farther away, that might minimize the crosstalk. But the problem is there are times when you want the qubits to influence each other. So one of the most important aspects of these things is called a two-qubit gate, which you have one qubit control a particular operation that may happen on the other on the qubit right next to it. So you really do want the qubits close to get as possible with each other in order to make these two qubit gates as good as possible. Because the other issue besides coherence is this thing called gate fidelity. And to give an example, a very common gate is in the quantum world is called a C naught gate, where essentially if qubit number one is at a 1, it'll flip the state of qubit number 2, and if qubit number 1 is in the state of 0, it won't do anything to qubit number 2. So that's a very, very common thing. It's very similar to an exclusive OR gate in the classical computer world. But today, people are building these things, but they're only getting reliability levels, or what's called gate fidelity levels, roughly in the 99%, 99.5% level, which means that 1 out of every 100 times or 1 out of every 200 times, even though you told the qubit to do something, it didn't do it. It made an error. And that's a real challenge. And of course, if you have multiple ones of those stacked up, even though you may only have an error of, let's say, 0.5% each time, if you stack that up, 100 times in a row, you're basically going to get, random information out of it. It won't be any good. In comparison, in a classical computer, what would be the equivalent of the gate fidelities, you could have your laptop or a semiconductor gate, a classical gate, run for a million years without ever making an error. So the reliability is so much, much better. So again, that's part of the challenges that people are working on to improve those gate fidelities so that you can process more complicated algorithms over a longer period of time.
What about the software that runs the computers themselves? Is that of a special breed? Is it very different?
So there's been a lot of work in terms of software, and one of the things that a lot of companies are doing, including Microsoft and IBM and others, they're trying to make the software as easy to use as possible. When I first started looking at this thing 4 or 5 years ago, there were very few software libraries available. Basically, you had to program everything at a very, very low level using these very specific gates that I was just talking about. And over the past 5 years, what many of these companies have come up with is software that's essentially based on extensions of a programming language like Python. So that if you're a good Python programmer, you are able to put together pretty quickly a software program, and it's been supplemented by a lot of libraries. There are some common routines that people are using these days, things like Shor's algorithm, for example, or variable quantum eigensolver, many other things, and they're packaging them together as libraries. So it is a lot easier now for someone to program these things. It's still not super easy, but it's a little bit easier because they can basically program in various platforms using an extension of Python, calling on these various libraries to do what you want to do. In addition, there's another challenge there, is that there's many companies out there that offer quantum computing hardware, and none of them are compatible. It's sort of like the early days of computing, where you had IBM and Univac and Burroughs and Honeywell and all these companies that were offering classical computers, but they all used a different instruction set. and you needed some way to commonize it. And in the classical computer world, people started developing programs like Fortran, and each company came out with something that would take a Fortran source program and compile it to their specific machine. Well, that same thing is happening now in quantum computing. There are companies out there that are offering what the term that they use is called hardware agnostic software, such that you can program in a relatively higher level language like I was describing before, and then they will compile it to a very specific machine. If you're using an IBM machine or a Google machine or a Rigetti machine or an IonQ machine or a Honeywell machine, it'll compile it to the specific instruction. I'll call it the instruction set or the gate operations that particular machine can do, and that is really helps the industry a lot because it allows people to develop one algorithm or one program and then try it out on a couple different platforms to see which platform works the best.
So I guess it's going to be a race to see which company is really going to be the new IBM or Microsoft or Apple of quantum computing, right?
Yeah, it is, pretty competitive these days. And, the interesting thing is that all these companies, they're using different technologies, and some of them are quite different than each other. So the analogy I would make is to some of the early days of the semiconductor industry, maybe 40 years ago, where there were a lot of different proposals for what's the best way of making a semiconductor. There was something called bipolar technology, there was NMOS technology, there was CMOS technology, gallium arsenide technology, and there were a lot of different companies who were looking at how do you build these things. And for a while, many of them were running at the same time, and eventually where we are today is ultimately the CMOS technology went out. CMOS is by far the dominant, although some of these are still used in a few cases. But the quantum computing technology is sort of in the era now similar to the early days of semiconductors, because you have the superconducting technology, you have photonic technologies, you have ion trap technologies, you have cold atom technologies, and you have others. And I keep track of all of those on my website. And no one really knows which technology is going to win out. So you have a lot of different companies working in a lot of different areas. I actually think that's healthy for the industry because ultimately the competition is there so that the strongest technology will ultimately win out. But people are taking a bunch of different approaches, and that will sort of assure that the strongest technology will ultimately win. But no one really knows which ones it's going to be right now.
Well, currently, when a company says they have a 50 qubit system or however many qubit system, I mean, how close are we to commercialized use of any quantum computer, even a really low level one, just a few qubits? Are we years away, or do you sense that we're close?
We're relatively close. So the milestone that people are looking for is something called quantum advantage, where they are able to utilize a quantum computer to solve a commercially relevant problem that cannot be solved with a classical computer. Whether it's something like a finance optimization or drug discovery or some logistics optimization. We're not quite there yet. Google did announce last year what I would call a stepping stone to that. They announced something called quantum supremacy, where they basically took a specific problem that they called an artificial benchmark that they created specifically to show that their quantum computer could do something that a classical computer could not do or would do very, very slowly. And they took that problem and they actually did very good engineering work. They built their 53 qubit quantum computer. They did a lot of benchmarking with that, both the quantum computer as well as the Summit supercomputer, which is the world's fastest computer. It's at I believe it's Oak Ridge National Lab, and they demonstrated that their quantum computer could solve that problem faster than the classical computer. And the reason I call it a stepping stone is because that problem that they had really does not have any commercial relevance. It was a specific problem made up for this test, and that's good. But the next step is this thing called quantum advantage. So people believe that we will start seeing various commercial applications start to trickle out over the next 2 to 5 years, probably with quantum computers that are maybe in the 100, 200, maybe 300 or 400 range, just a little bit larger than what we have today. And that will be very exciting, because at the end of the day, although it's generates a lot of research, a lot of good papers and PhD thesis on quantum computing, the reason both government as well as venture capitalists are putting money into this is because they want to do something commercially relevant, something that can give them a return on their investment. And you have to do something that's commercially relevant in order to do that. And I do think we'll see that in the next 2-3 years.
This is probably the last question. What will it look like even when we get some commercial use? Will it be like renting time on a quantum computer? Will big corporations do that? Do you think it will ever be at a point where, I don't know, there's somehow desktop quantum machines, or who knows if it's even cloud computing that where smartphones could access quantum computing applications?
Yeah, I think for the foreseeable future, all the access to the quantum computers will be over the cloud. These are large machines, like the original mainframes. You saw pictures of those from the 1950s and 1960s. They're very large. They require a lot of tender loving care. They require frequent calibration. You have these very expensive refrigerators that cost over $500,000 each. So the way the industry is being set up is the access is going to be over the cloud. You may be able to access it, from a smartphone or a laptop. In fact, people can do that today with various cloud setups. But you will not find a quantum computer on your desktop or in your pocket anytime actually within our lifetimes. I think the technology is still going to be very, very complicated for many, many decades. But by using it over the cloud, you're able to get the benefits without actually physically having it, in your office or on your desk.
What's the best way for people to keep up with the latest and follow your writing and your reports?
So I do maintain a website. It's called the quantumcomputingreport.com. Quantum Computing Report is all one word. And you can go to that website, and right on the home page, you can sign up for a newsletter. So what I do is every week I will publish a newsletter that describes some of the latest changes, the latest news events, or the latest new startup companies that I've added on the website over the past week. And then you can, once you get that email, you can click on the items that interest you, and it'll take you directly to the item that you're interested in. So it's a very good and efficient way of keeping up with what's happening in the industry without having to browse, a million pages.
Great. Well, Doug, thanks for coming. I appreciate it.
Okay. Well, you're welcome, Rich, and thanks for inviting me.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.